Lesson and welcome to my channel Concept of Mechanical Engineering. We are studying thermodynamics, and in thermodynamics in the previous class we have seen property of a system, intensive property, extensive property, and then we have studied specific quantity and some important points with respect to property. Then we have studied process, state of the system. In process we have seen reversible and irreversible process. Now today we will see quasi-static process. So let's start with quasi-static process. So what is quasi-static process? A process which is carried out very slowly, such that in each state the system is in thermodynamic equilibrium. So a process which is carried out very slowly with small gradient, and in each state the system remains in thermodynamic equilibrium, is called a quasi-static process. So we will understand it with an example. Let us consider a system, a gas cylinder. Let's see, this is a piston cylinder system. This is our piston and this is cylinder where we have gas. These all are gas. So, and which is here that we have kept differential weights, very small weights. Let's see this one. These are differential weights. So this is the initial condition of the system. With weights, with differential weights. So if we see, if we remove these weights one by one, let's see what happens. Here this is the initial condition of the system. The same we are drawing here, the same system. So let's first remove this one small weights. As we remove these weights, then this piston will go further up. This is the system. This is done very slowly. So after moving this piston this distance, the system comes to equilibrium. That is, there is thermodynamics equilibrium is achieved. After that we remove another weight. Again the piston will move up, and in this state also the system will comes to thermodynamic equilibrium. Again we will remove this weight, the piston will move a little bit up, and since the process is very slow, so it will get time to achieve equilibrium. The system will comes to thermodynamic equilibrium. Similarly we will remove this, the piston will move here. We will remove this, the piston will move here, and finally this will remove this one, the piston will comes here. So what we see, since we are removing this weights one by one and in very slow manner, so that after removing one weight the system comes to thermodynamic equilibrium, then the another weight is removed. So this process is carried out very slowly. We can see this in PV diagram. This is our pressure volume curve. We will achieve this curve. Initially we have pressure P1, volume V1, temperature T1. This is initial condition, and finally we have achieved pressure P2, volume V2, and temperature T2. This was the initial condition where P1, V1, T1, and this is the final condition. Here the pressure is P2, V2, and temperature is T2. So if we see that initially we have pressure, volume, and temperature. After removing this first weight, the system goes this is the piston that moves up. So we will have this curve here as this point, and after achieving equilibrium we have removed the next weight. Again the system goes to thermodynamic equilibrium. Similarly, in each step the system is under thermodynamic equilibrium, and since we have removing the weights, the pressure is decreasing and volume is increasing. We can see from the graph also. So in each state, these are the states, equilibrium states. So in each states the system is in thermodynamic equilibrium. So we can now write some points regarding this. A process which is carried out very slow manner with small gradient is known as quasi-static process. We can note that in quasi-static process the system exists in each state in thermodynamic equilibrium. This was the note 1, and note 2, a frictionless quasi-static process is a reversible process. So a frictionless quasi-static process is a reversible process. So a frictionless quasi-static process is a reversible process. So we have seen that what is quasi-static process. It is a process which is carried out very slowly, such that in each state the system remains in thermodynamic equilibrium, and a frictionless quasi-static process is a reversible process. Now we will see cyclic process, that is thermodynamic cycle. So a system is said to have undergone a cycle when initial and final points are same. So a cycle is said to be, so that is a system has undergone a cycle when initial and final points are same. Let's see this. We have started a process from here and it is ending here. So the initial state was this and the final was also the same. This is, so this has undergone a cycle. Let us consider another example. A process from this 1 to 2 is a process, 2 to 3 is another process, and 3 to 1, this is another process. Since we have started from state 1 to 2 one process, state 2 to 3 another process, and 3 to 1 another process. The initial stage was this and the final stage is the same. So this has undergone a cycle. This is called as cyclic process or thermodynamic cycle. A system is said to have undergone a cycle when initial and final points are same. For a cycle, change in property is 0. So a system is said to have undergone a cycle when initial and final points are same, and for a cycle change in property is 0. Gibbs phase rule. So let's see what is Gibbs phase rule. F plus P is equal to C plus 2, where F equals to degree of freedom, P is equal to number of phases, C is equal to number of components. Degree of freedom. Let's see degree of freedom. It is the number of independent variable required to define state of system. It is the number of independent variable required to define state of system. Here independent means intensive, variable means property. So degree of freedom, it is the number of independent variable required to define state of a system, or we can say it is the number of intensive property required to define state of the system. State of the system means condition of the system. To define the condition of the system, that is the state of the system, what is the number of independent variable required? That is called degree of freedom. So degree of freedom can also be written as number of intensive property required to define state of system. This will be understood easily if we will take an example. Let us consider one container which is having O2 inside. So this container is having oxygen gas, that is it is having phase 1, since oxygen is present in only one phase here in gaseous form. So number of phase is 1, only one oxygen is there, so number of component is also 1. Using the formula F plus P equals to C plus 2, F plus 1, 1 plus 2, we will get degree of freedom as 2. So here the minimum independent variable required to define the state of the system is 2, because degree of freedom is here 2. We can understand it easily by, see, this is PV equals to MRT. So P, if we put bring M here, V by M, RT, volume per unit mass, this is specific volume, we can, this is denoted by small v, equals to RT. So if we know two variables, like if we know temperature or pressure, because R is a constant, this is a gas constant, this is constant here. So if we know the temperature or pressure, we will know this specific volume. If we know a specific volume, we will know pressure and if we know a specific volume and temperature, we will know the pressure. So this is having 2 degrees of freedom. We will take another example. Let's see phase change. Phase change. For phase change, H2O is steam and H2O liquid form, that is water. So here we have component, number of component as 1, because this is only the forms of water, so only one component is here, so number of component is 1, and it is having 2 phases, one is in gaseous form and the other is liquid form. So phase is, number of phases 2. F plus P equal to C plus 2, that is F plus 2 equals to 1 plus 2, that is F equals to 1. So this is having degree of freedom 1. During phase change, degree of freedom is 1. PV equals to RT, R is constant, and since it's having degree of freedom 1, that is if we vary one variable, we will get the value of other variable. We know that in during phase change, temperature remains constant. So since temperature is constant, there is only 1 degree of freedom. We can better understand this with the TS diagram. If we see TS diagram for phase change, this is critical point. For particular pressure, we will have a saturation temperature as TS1. If we will change the pressure P2, we will have another saturation temperature. So there is only one saturation temperature. Saturation temperature for one saturation pressure. So there is only one saturation temperature corresponding to a saturation pressure. So for one saturation pressure, we will have one saturation temperature, and for another saturation pressure, we will have another saturation temperature, since the degree of freedom is 1 for phase change. For water, temperature, critical point temperature is 374 degrees centigrade, and critical point pressure is 218 bar to 222 bar. Now let's take another example. Consider a container having water in three forms: H2O in steam form, H2O in water form, H2O ice form. Here number of component is 1, number of phases is 3. So F plus P equals to C plus 2, F plus 3 equals to 1 plus 2. That means degree of freedom equals to 0. That means all intensive properties are fixed. All intensive properties are fixed. That is triple point of water. So this is the triple point of water. We are having steam, water, ice, all three phases present. So due to which the degree of freedom is 0. That is all intensive properties are fixed. Since the degree of freedom is 0, so all intensive properties are fixed, which is called triple point of water. We will see at triple point of water, temperature at triple point of water is 0.01 degree centigrade. It is fixed. That is at triple point the temperature of water will be 0.01 degree centigrade. If we want to convert this in Kelvin, this is the formula for conversion of temperature from degree centigrade to Kelvin. Kelvin equals to 273.15 plus degree centigrade. So if we want to convert degree centigrade to Kelvin, we have to add 273.15 in the degree centigrade. So the temperature will become, it is 273.16 Kelvin. So in Kelvin, the triple point temperature is 273.16 Kelvin, and triple point pressure is 611 Pascal. So we have seen that at triple point degree of freedom is 0. That is all intensive properties are fixed, and that's why the